All right, welcome to the advanced tutorial for our nuclear reactions practice. If you're on this video, you should already be fairly comfortable with adding up protons and neutrons and figuring out how many of each you have in an atomic model, like for example, this one for uranium-238. So this video is more about dealing with free neutrons, with radiation, and just with more, in this case, it's more products or more reactants. There's just more to keep track of here. And these problems are more difficult. So we're going to more or less start out the same way, just sort of doing some basic bookkeeping of what protons and neutrons we have. And in this case, it's going to be easiest to start with our reactants. This is a fission reaction. We have the fission of uranium-238, and it turns into neon-20, something that we're trying to figure out, which hopefully is one of our 4 answers over here. Plus, this is 3 free neutrons, plus some beta radiation. None of the problems in the actual practice are quite this complicated, but I wanted to incorporate elements of everything into just one example. So again, we're just going to start with some bookkeeping of what we have, of what we already know we have in our reactants and our products. So let's start with our reactants. It's uranium-238. Uranium, from our periodic table, we know has 92 protons, always, forever, no exceptions. Uranium-238, that mass gives us the number of neutrons, which is going to be 146. If you add 146 and 92, you get uranium-238, or you get just 238. If you have 92 protons, it's uranium. Now let's check out our other side, starting with the easiest thing to deal with, the most straightforward, which is neon-20. Neon always has 10 protons. Neon-20 means that we also have 10 neutrons. 10 and 10 equals 20. Those free neutrons, this can happen, and with something like the fission of uranium, sometimes we do just have neutrons that aren't associated with any atomic nucleus. They're just free and floating around. We use the lowercase letter n to symbolize neutrons. A lot of students will get confused, see that n, and think, oh, that's nitrogen. It's not. Nitrogen can't have a mass of just 3. Nitrogen has 7 protons, so its mass is always going to be more than 7. So those are 3 separate individual neutrons, each with a mass of 1. Instead of writing out sort of all of that, we just say, okay, we have 3, lowercase n. That tells us, okay, I'm dealing with neutrons. They don't stick together. How many do I have? Well, I look at that mass. Sometimes it'll be 1. It means I just have 1 neutron. Sometimes it'll be 2. It means I have 2. Sometimes it'll be 3 or more. That's just telling me how many neutrons I have. So I have 3 free neutrons not associated with the neon or with whatever mystery element I'm trying to figure out is missing from this reaction. I also have some beta radiation. Beta radiation, again, is going to make this a little bit trickier because what's happening is one of my 146 neutrons from my uranium-238 is turning into a proton. What that means is that on the right side of this equation, in my products, I'm not going to have 92 protons and 146 neutrons. Instead, I'm going to have 93 protons and 145 neutrons. A neutron becomes a proton. It loses a negative charge, which means it goes from a charge of 0 to a charge of +1. So this beta radiation means that my numbers for protons and neutrons are a little bit different, and I've got to take that into account when I figure out what's missing. Okay, so what do I have so far in my products? I have 10 protons plus 13 neutrons. Again, the total number that I'm going to have is 93 protons and 145 neutrons. It's not the same because of that beta radiation. So whatever this thing is has to have 83 protons. Why 83? Well, 83 plus 10 is 93, And as I just talked about, that's how many protons we're going to have. So what has 83 protons? Bismuth. Again, always, forever, you look that up on the periodic table. You don't need to memorize it. There are never any exceptions to the number of protons matching the atomic number that's on the periodic table. How many neutrons do we have? Well, between my 3 free neutrons plus the 10 in neon 20, that gives me 13. I need to add up to 145, not 146, because that beta radiation. So that means I have 132. So this bismuth atom has 83 protons, 132 neutrons, which means it has a mass of 215. It is bismuth 215. I look over at my answers, and that is one of my options, so that is the correct answer. One thing to notice about the beta radiation, it changes the number of protons and neutrons, but it doesn't change the total mass. If I add up 10 plus 10 plus 3 plus 83 plus 132, I'm going to get 238. The type of radiation that would appear to change this is alpha radiation. Alpha radiation, remember, is a helium-4 nucleus. It has 2 protons and 2 neutrons. So you may see that the mass number sort of appears to change if you have alpha radiation, but it doesn't because that alpha particle has a mass of 4. Just keep that in mind if you see it. So this example, I think, covered just about everything that you would need to know. Again, the different types of radiation, like alpha, positron, gamma, we're not really going to worry about because it doesn't change anything with the nucleus. So just alpha, beta, positron, gamma, free neutrons, dealing with multiple products, all of that we covered. So at this point, you should be able to answer all of the questions in our practice. So good luck again.